Alright, in this module we're going to go ahead and do feedforward control. This one's a fun one. So far all we've been doing is feedback control, controlling based on our process variable and our set point, and the difference between our process variable and where we want to be. In feedforward control, rather than control only based on our set point, we also control based on disturbances that we've measured, and then we control based on the disturbance's anticipated effect upon our system. For example, if we have heater 2 heating up, we can anticipate how that will affect heater 1. So we'll go ahead, and this actually has two parts. In the first portion, we'll test the performance of temperature 1 set point change from an ambient temperature to 40 degrees at 10 seconds, and adjust heater 2 from 0% to 100% at 200 seconds and back to 0% at 400 seconds. This test will go all the way to 600 seconds. We'll look at that step change from 0 to 100% on heater 2 and how that affects the performance on heater 1. Then we'll control again using a PID controller based on that. So we'll go ahead, we'll look at the disturbance gain. The only thing you have to worry about here, so you can see we connect to the lab, and first what we're going to do, I should back up. That is our end goal, to be able to control based on that disturbance gain. First we need to know how the disturbance affects our controller, how the temperature on temperature 2 affects temperature 1. To do that, we'll do two things. We'll look at the disturbance gain and the process gain and compare those to create the feed-forward gain. Really quick, let's just think about how our units work here. The disturbance gain, KD, is, again, we always think of like how input relates to output. So the KFF, if we think about our process flow diagram, it comes in right here along with the output, and it's going to, the output should be, this is the process right here. Right here is the temperature sensor. So what we need is some gain that converts the disturbance to the output temperature, like the increased temperature, the effect on the temperature. So that's what's over here, temp. That's where our K feed forward goes. And our disturbance gain measures the change in disturbance based on that. So let's go down and let's look at our system now. We're going to create zeros for time, T1 and T2. We're going to set Q2 to 100, and we're just going to measure time for 600 seconds and look at the effect. We're going to print out T1 and T2, and we're just going to display it to the console. I'm going to pause for 1 second. We're not going to be doing anything fancy here. We're just going to record time. So our KD is equal to the change in temperature 1 over the change in temperature 2. I'll just write that again real quick. KD is equal to delta T1 over delta T2. So that we can measure if there's a change in temperature 2, we multiply it by KD to get the effect on T1, which is what we're controlling. So another way to think of this is the delta of our process variable over the disturbance variable. And that's, I think, the better way to think of it, a little bit more general. Then the K feed forward is how we're going to counteract that disturbance in our control settings. So instead, we're going to counteract that by doing the opposite. That's why there's a negative right there. And then we have KD over KC. So let's go ahead and let's look at how we, let's do our step test and see what the results are. So I'll take off the writing. We have it filled in. Let's go ahead. Let's just run this block. Connecting to the temperature control lab, and we're off to the races. You can see the two temperatures, and we'll go ahead and we'll just pause for a bit. Alright, here we have our results. We'll notice that I actually didn't find KC before we have this all, And so I'll go ahead and just, probably up here is a good place to define it earlier. Probably do Kp is equal to something. Kp is equal to 0.9. Then Kc is equal to 1 divided by Kc. To do that easier though, or to do that for what we do rather than rerunning it all, we'll do Kc is equal to 1 divided by 0.9 in our command window. And then Kff is equal to negative Kd divided by Kc. And now both of those will be in our system. So negative 0.29. Our Kd is equal to 0.32. So for every degree that the second heater goes up, our first heater will go up by 0.32 degrees. Let's now look at our TCLab PID with feedforward simulator. Our Kd, if you'll remember, was 0.3. Our Kc is way down, 0.1. And then we can play with our tau I and our tau D. So we can see here we have the effects of the two on each other, because you can see T2 going up when it's not on, and we have it turning on and going high, and then coming back down. We'll make our graphs a little bit bigger. Let's consider, looks like our integral control could be a little bit more enforced. And also I think turning our Kc up could help. So we have some overshoot and we're going to have some oscillations because of that. Would it be better to turn down the integral control and keep Kc high? I think it would. So let's see. We turn Kc higher, we're going to have more oscillation. So we turn Kc down, and that's what this process really is. You know, it can also change the disturbance or the derivative control. And we'll just play with things till we have something we like. That heater setting, you know, you can definitely tell when you're looking at the heater setting that there's some oscillation going on there. So my thought is back off on the integral control. Again, this tuning process is an iterative process. Ooh, I like that. So maybe let's go with that. It seems to respond fairly quickly and then reject disturbances. You notice that most of that we're looking at tuning the controller, but it rejects the disturbances pretty well, it seems. If we look at our heater setting, you'll notice during this time where it's remaining rather constant, actually in this one as well, it doesn't change the set point. So let's go up here. We want the set point to go to 40 at 10 seconds. Okay, let's read it again. Test performance to heater 1 set point change to 40 degrees at 10 seconds and adjust heater 2 from 0 to 100% at 200 seconds, heater 2 back to 0 seconds. So we're only changing, yeah, it should be constant, never mind. We're good. All right, let's go ahead, let's try it out. Our Kc, let's look at what they are. So we've got 10, 105, 9, and 0.3. 10, 105, 9, and I'll leave this at 0.2903. I like using what we did. Then we've got our parameters. We're going to pass them to now our PID feedforward controller that incorporates all of that. We have our variables, and our set point includes the set point change, and our Q2 anticipates that from 200 to 400 is going to be equal to 100. Finally, let's go ahead and let's look at our PID feedforward simulator. No, not the simulator. We want the actual one. Our feedforward controller, there we go. So it returns the output and the error, which is what we like. Or it's good enough. If we know what it returns, we can work with it. Let's look at the derivatives. I always like making sure, again, like I said, if we're taking the derivative of the process variable, we want to make sure it's negative, which it is. We have the feed forward times the disturbance minus PV is our P, and we have it all together right here. And we have some anti-reset windup. So it looks like a good plan. Let's go ahead now. I'm going to go ahead, let's see. Are we already connected to the lab? We connect to lab right here. So let's go ahead, let's see if we're connected to lab. Lab equals TCLab. And we're connected now. So let's see, lab.t1. We're at 24 degrees. Sounds like we have it turned off right now. So I'm going to go ahead and close, or clear, not close. Clear lab. And we'll go ahead and we'll run this test now. And we'll see how well our feedforward control runs. It's connected to the lab successfully. Do we have it set to graph? We do. So let's go ahead and check out our graph. We're going to change the set point in just a moment. There we go. Now we have them both. T1 is in the dots in red. T2 is the dots in blue. All right, we'll pause the recording and we'll see how we do. So there we have it. Let's look at our results. We have temperature 1 progressing towards 40, a little bit of an overshoot, so we probably want to tone down the gain, the process gain. Not the process gain, but the proportional constant. If we look though, we can see some change to T2 because of T1. At 200 to 400, it turns on and it goes up. And you can notice that rather than react to a high temperature per se, the heater goes down on its own based on feed-forward control. The value drops lower than it was to 0 at one point, and then back up as T2 turns off and it's receiving less heat. And it stays very close to that line of 40. So you have it. We've done feed-forward control in MATLAB on the temperature control lab.